Okay, good afternoon, Cappuccino. Sorry I'm so late in getting this up. This was supposed to be up yesterday, and now it's Tuesday afternoon, but c'est la vie. Okay, so I had a lot of people having a hard time with investigation number 3, so I want to go over that first. And now I can't find my pencil. That's excellent. So on investigation number 3, we're actually trying to prove this formula right here. So in order to do that, I'd really love to have my pencil. Guess that's not happening today. In order to do this, they're going to have us do something kind of weird. They're going to have us take the sum of the first 5 terms of a geometric series. So right here, the sum of the first 5 terms is the first term plus the second term plus the third term plus the fourth term plus the fifth term. And you get each term by multiplying the previous term by the common ratio. So there's our r keeps getting an extra exponent on it. Okay, so what we're going to do is we are then going to take this expression, the sum of the first 5 terms, and we're going to multiply it by the common ratio. Why? Why not? So this is kind of a thing that happens in mathematics where you're trying to prove something. You end up doing something a little unexpected, but it helps out in the end. So this is one of these moves that is going to help us in the end to come up with a formula. So for part 1 here, we're going to take the sum of the first 5 terms, and which is equal to u sub 1. Let's just write it again. And we're going to multiply it by r. So I'm multiplying the sum of the first 5 terms by r. So that means everything on this side of the equation also has to get multiplied by r. So that's what they want us to do here on problem 1. And let's go ahead and we are going to distribute this to simplify it. So I'm going to distribute this r to every term inside the parentheses here. So every term here is going to get multiplied by r. So r times the sum of the first 5 sequences gives us u1 times r plus u1 r squared plus u sub 1 r cubed plus u sub 1 r to the 4th plus u sub 1 r to the 5th. Okay, so we still have the same number of terms, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, but they've all just been multiplied by r. So that's part 1. So then they say, okay, now that you've done that, let's write an expression for r times the sum of the first 5 terms minus the sum of the first 5 terms. And you're saying, why are we doing that? Again, just bear with us. This is kind of a common mathematical trick in order to prove that a formula works. You end up multiplying by something, adding something, subtracting something, so that you can then end up proving something else. Okay, so I'm going to have this guy, which is all of this, and I'm going to be minusing this guy, the sum of the first 5 terms, which is this. So I'm going to write this out. Let's see, how should I write this out? I'm going to stack them, okay? So this is the first one, u sub 1 r plus u sub 1 r squared plus u sub 1 r cubed plus u sub 1 r to the 4th plus u sub 1 r to the 5th. And I'm going to minus now this one, and I'm going to put it underneath. I'm going to minus all of this. So each one of these terms is going to get subtracted. So I'm going to minus, I'm actually going to put it over here. Now I'll just put it here. I'm going to minus u sub 1, and then I'm going to minus u sub 1 r, and I'm going to minus u sub 1 r squared, and I'm going to minus u sub 1 r cubed, and I'm going to minus u sub 1 r to the 4th. Okay, because I'm minusing all of this, so you can think about it as negative 1 times the sum of the first 5 terms, which is this. So if I multiply each of these by negative 1, I'm going to eat these. Okay, so I now need to combine all my like terms. So u sub 1, is there another u sub 1? No, that's the only one. So I'm left with negative u sub 1. Okay, negative u sub 1 r. Oh, look, there's another u sub 1 r. Those are going to cancel out. Okay, so think about it. I'm taking this and I'm subtracting this. So these two are canceling out. These two are going to cancel out. these two are going to cancel out, and these two are going to cancel out. Okay, so this one is going to cancel with that, this one with that, this one with that. This one, it doesn't cancel with anybody, so I still have u sub 1 r to the 5th. So r times the sum of the first 5 terms minus the sum of the first 5 terms is the same thing as the opposite of the first term plus, basically this would be the 6th term. Okay? So that is part A. Find an expression in terms of u and r for that. Okay, and then they want us to find an expression just for the sum of the first 5 terms. So that means I'm going to take this and I'm going to get s sub 5 by itself. Well, how am I going to get s sub 5 by itself? I have 2 of these right now, so I'm thinking, oh, you know what? I can actually factor this out. Both of these terms have an s sub 5, so if I factor that out, okay, I'm now on part B. If I factor out my s sub 5, I'm going to be left with r minus 1. Okay, remember how I said this is like a times negative 1? So I have 2 terms. I'm parsing here like I like to do with my algebra classes. These both have an s sub 5, so I'm factoring out my s sub 5, and I'm left with r minus 1. Okay, so I can do the same thing on this side. They both have a u sub 1, so this is like negative 1, u sub 1. So I've got 2 terms. They both have a u sub 1. So I can factor out my u sub 1, and I'm left with negative 1 plus r to the 5th. Okay, so now I'm trying to get that s sub 5 by itself, so I'm going to divide by r minus 1. So I'm going to divide both sides of my equation by r minus 1, and that leaves me with the sum of the first 5 terms is equal to u sub 1. I'm going to rewrite this. I don't like having a negative 1 plus, so I'm just going to use the commutative property of addition to switch the order here. That's r to the 5th minus 1 over r minus 1. So that's part B. So I've now gotten the sum of the first 5 terms all by itself. Notice this number here is the same as this number here, so I can generalize part B to say that s sub n is equal to u sub 1 times r to the nth minus 1, all divided by r minus 1. And here it is. This is generalized, so when we generalize, we take out, this was for specifically for the first 5 terms, but it would work for any number of terms. It doesn't matter that this was a 5. Just notice that's the same number here as here, so we can replace that with the letter n. Okay, so that was investigation number 3. And so I know a lot of people were having a hard time with that, so I hope that helps. All right, so the thing that we're going to be taking notes on today is the sum of an infinite series, and I just want to look at this problem right here real quick. First of all, in investigation 4, in the first part of it, you should have recognized that if you found these terms, u sub 10, u sub 15, u sub 100, they got really, really big. Whereas when you change the r to 0.9, these terms got really, really small. They got really tiny. So what's the difference between these results? Well, when r is greater than 1, the terms become bigger and bigger, whereas when r is less than 1, it becomes your terms become smaller and smaller as you go along. That's the main difference. Okay, so let's have a look at this problem right here. So we have this square, which is 1 meter squared. So the whole thing is 1 meter squared. We cut it in half, and the area of this part is going to be our first term of our sequence. So our first term in our sequence is 1/2, because if the whole thing is 1 meter squared, this is half a meter squared. Okay, so our first term is 1/2. Then we're going to cut it in half again, and if we cut this in half, we would get this piece, and so that is 1/4 of the whole thing. Okay, and then if we took this and we cut it in half again, we would get this piece, which is 1/8. So our sequence is 1/4, 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1 over 128, and we could keep going. So if we were to add all of these areas together, so I keep cutting in half, keep cutting in half, keep cutting in half, keep cutting in half, and I keep adding those together, we're just going to keep filling in this region. Are we ever going to go outside this region? Are we ever going to like pop out and start growing again? No, we're getting smaller and smaller pieces, and it's always going to stay inside of this region. So if I add 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus 1 over 128, if I keep adding these together, it's going to fill in all of this area, but it's never going to go outside. Therefore, we have a limit of 1. The area cannot be any bigger than this square, because we're filling this in, but it's never going to go outside of it. So there is a limit. We're never actually going to completely fill it either, but it is going to have a limit of 1. So because the r is less than 1, the absolute value of r is less than 1, in other words, it's a fraction, somewhere between -1 and 1. When r is in between -1 and 1, your terms are going to get smaller and smaller and smaller, and so when that happens, they're going to converge to a single solution for adding them together. You're going to converge to a number, and it's a limit. You're never actually going to get there. If you add these all together, you're never actually going to be able to fill the square, but for all practical purposes, you will. And once you've filled the square, what's the area? The area is 1. So if we use this formula and we say that n is infinity, then think about this. R to the infinity. So r is 1/2. 1/2 multiplied by itself an infinite number of times. What's happening there? Okay, where's my scratch paper? So if I take r to the n, and r is a fraction, say it's 1/2, and n is a really big number. Let's say it's, we don't even have to do a really big number. Let's just say it's 10. What's 1/2 to the 10th? Okay, if I take my calculator and I have 1/2 raised to the 10th, look at that. It's 9.8 times 10 to the -4. 9.8 times 10 to the -4. Okay, so that would be 0.00098. Okay, that's just to the 10th. What if I take it to the 100th? 0.5 raised to the 100th. That's 7.9 times 10 to the -31. I don't even want to try and write that down. Okay, that is so many zeros in here. There would be 30 zeros in here before I get to the 7 and the 8. Incredibly small number. Okay, so when I have 1/2 raised to the infinity, a really huge number, so huge we can't even write it down. What am I going to get? It's going to get incredibly small, basically 0. Okay, so when I take the limit of 1/2 to infinity, it basically equals 0. So here on this equation right here, I have the sum of my terms is equal to the first term times 1 minus r to the n over 1 minus r, okay, which we proved in investigation 3. When I take that and I say that r is a fraction, okay, and n is infinity, if I take the limit of this, okay, so if I take the limit as n goes to infinity, what's going to happen here? This is going to become 0. So my fraction raised to infinity, this, the limit of that, as n goes to infinity, this is going to be equal to 0. That's just going to be 0. So I end up with u sub 1 times 1 minus 0 over 1 minus r. Okay, 1 minus 0 is just 1. 1 times u sub 1 is u sub 1 over 1 minus r. So this is the formula we're going to be looking at today. This is the formula for the sum of a sequence, a geometric sequence, or a series, when we go to infinity. Okay, the sum as n goes to infinity of a geometric sequence, but r has to be a fraction. R has to be, oops, I put it in the wrong place. It has to be between -1 and 1. Another way of writing that is the absolute value of r has to be less than 1. That's the same thing as this. Okay, so that's what we're doing. So back to our notes. If we go to our notes, we are going to do a couple of problems with this formula. All right, so infinite geometric series. The sum of the series as the number of terms goes to infinity is equal to the first term. Remember, u sub 1 is the first term, divided by 1 minus r, and r is the common ratio. And this only works if the common ratio, the absolute value of the common ratio is less than 1. Okay, so let's do an example here. So find the sum of the infinite series, and 1 million plus 500,000 plus 250,000, etc. So this is called a series because it has plus signs. Okay, if it doesn't have the plus signs, if we had commas instead, oh, I found my pencil, thank goodness. This is called a series. If it was just like this, 1, 2, 3, 4, 5, 6, comma, if it just has commas, so we just have terms and they're not being added, dot, 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 this would be called a sequence. Okay, so let's write that down. This is a series. This is a sequence. So just a little vocab development there. Okay, series versus sequence. This is a series because they're being added. This is a sequence because it's just a list of numbers. Okay, series versus sequence. All right, so we know it's going to be geometric. So what is our r? Let's figure out what our r is. So we know that 1 million times r is going to be 500,000, and 500,000 times r is going to be 250,000. So we can solve for our r by saying, all right, 1 million times r has to give me 500,000. So to get r by itself, I'm going to divide both sides by 1,000,000. So r is equal to 500,000 divided by 1,000,000. Okay, I can divide these by 10, divide by 10, divide by 10, divide by 10, divide by 10. I'm left with 5 over 10, which is 1/2. Okay, so my r is equal to 1/2. So now I'm going to use my formula. The sum of, as n goes to infinity, okay, so as n goes to infinity, the sum of an infinite series, so n is going to go to infinity. If I kept going on this pattern and kept adding all the way to infinity, what am I going to get? So I'm going to get u sub 1 over 1 minus r. U sub 1 is the first term, so that would be 1 million divided by 1 minus r, and r is 1/2. So I can simplify that. 1 million divided by 1 minus 1/2 is 1/2. So 1 million divided by 1/2. Now be careful here. 1 million divided by 1/2 is not 500,000. Okay, we got to change this. We can rewrite it as 1 million times the reciprocal. Okay, we're dividing by a fraction. Okay, this is the same as, maybe I should write that out. This is the same as 1 million divided by 1/2, so we multiply by the reciprocal, which gives us 2 million. The answer is 2 million. So if I start with $1 million, say I get $1 million one week, the next week I get 500,000, the next week after that I get 250,000, and then the next week I get half of that. How much money am I going to end up with if this goes on forever? I'm gonna be approaching 2 million. I'll never actually reach 2 million. I'll only be approaching it. Okay? So we say that the sum converges to 2 million. So we say it converges, it's convergent. The sum is convergent. This is important for math space. You're going to see this in math space. The sum is convergent. Okay, it's convergent. And we say we call this the limiting sum. The sum is convergent. It converges to 2 million. And this 2 million, this guy right here, is called the limiting sum. It's the limit. We are not going to ever reach it. If we continue this and keep adding them, we'll never actually get there, but we'll get really, really, really close. And that's called the limiting sum. Okay, and we say that this is convergent. All right, let's do another example. Here's our next example. Find the sum of the infinite series. Okay, so here is our series. So the first thing we need to do is we want to figure out what our what our R is, what's our common ratio. So I'm going to write it as this is a series, right? That's a series. I'm going to write it as a sequence. This is not a necessary step, but I'm just trying to keep reinforcing the vocabulary. Oops, sorry, you can't see what the problem was. Find the sum of the infinite series. This is a series because there are plus signs. I'm going to write it as a sequence, means it doesn't have plus signs. Dot, dot, dot. All right, so what is my R? So times by R times by R. So I'm going to have 0.001 times R is equal to 0.002. Solve for R, I get R is equal to 0.002 divided by 0.001, and that just simplifies to 2. Okay, so now I'm going to set up my sum of my infinite series is equal to u sub 1 over 1 minus R. So my u sub 1 is my first term, that's my u sub 1, so 0.001 divided by 1 minus R, R is 2. And I get 0.001 divided by 1 minus 1 is negative 1, which equals negative 0.001. Now, isn't that strange? How is it that I'm adding a bunch of positive numbers and I end up with a negative answer? What happened? Can you see what happened? Okay, why did this go wrong? Why is this giving me a crazy answer? Did I make a mistake? Yes, I did. I cannot use this equation. We cannot use this equation because look at my R value. R was equal to 2. This equation can only be used when R, the absolute value of R, is less than 1. So notice, this does not make sense. This doesn't work. Okay? The formula does not work. Because R is greater than 1. So we can't do this one. So what's happening here, if I add these numbers are getting bigger as I go. They're getting bigger and bigger and bigger. So when I add these and go to infinity, this sum is also going to go to infinity. So there is going to be no limit. Okay, this series has no limit as n goes to infinity. It has no limit. Okay, if we keep going and try and add these, it's just going to get bigger and bigger and bigger and bigger. It's never going to approach anything. It's going to go to infinity itself. All right? So the answer here would be it goes to infinity. It has no limit. Okay? It goes to infinity. So special vocabulary for this, it says the sum, we would say the sum, this one right here, the sum is divergent. Divergent. All right, because it approaches infinity or negative infinity. The sum is divergent. It approaches infinity or negative infinity. In this case, it approaches infinity because these are all positive numbers. But if this had been negative 0.001 plus negative 0.002 plus negative 0.004, it would approach negative infinity. Okay, so we say it's divergent. So this is an important vocabulary for math space today. All right, so that's it for the examples. Just a couple little tips. When you're working with sequences and series, first you want to make sure you identify if you're working with a geometric or an arithmetic sequence. Okay, so geometric has a common ratio. You're multiplying by the same number each time. Arithmetic has a common difference. You're adding or subtracting by the same amount each time. So super important, make sure that you confirm whether you're working with a geometric sequence or an arithmetic sequence, because that's going to decide which formulas you're going to use. Then, next, identify if you're being asked to find a term in a sequence, or if you're finding the sum of the terms in a sequence, because there's different formulas depending on what you're being asked for. If you're asked to find a term, you're going to use one of the formulas that starts with U sub n. This is for finding a term. And if you're being asked to find a sum, you're going to use one of the formulas that starts with S sub n. Okay, so back to the formula sheet. Okay, notice our formulas here. Two of them start with a U. These are if you're looking for a term. So if you're looking for a term, you're going to either use this one or this one. And notice the first one is for arithmetic. So that's the first tip. Was it arithmetic or was it geometric? Okay, and then this one is for a geometric term, right? Now, if you're asked for a sum, there's actually three. There's three formulas. The first one is for the sum of an arithmetic. So if you've decided that your sequence is arithmetic and you're finding the sum of it, you're going to use this formula or this formula. Okay, they're equivalent. Now, if it's geometric, you're going to use this formula or this formula. Again, these two formulas are equivalent. And then if it's an infinite geometric sequence, you're going to use this one. See how it says sub-infinity, the sum sub-infinity? You are going to use this one, but remember R, the absolute value of R has to be less than 1. And we ran into that weirdness on this, okay? So watch out for that. All right, so that's it. On your mark, get set. You're going to go to math space. Tomorrow I will have office hours at what time? 10:30? So if you have questions, come to that. I'm still working on what our final exams are going to be like. So for my seniors, hopefully by tomorrow I'll have a better idea of what the final exam is going to be like, but it is going to be in math space. And then for my juniors, your final exam is going to be paper and pencil, and it'll be in 2 weeks, like 2 weeks from tomorrow, I think. So that's about it for today. Oh my gosh, this video is almost half an hour long. Sorry, watch it at double speed. Too late now. It's the end. All right, see ya. Bye-bye.